So we are given those components. And we want to convert the information into the new coordinate system. And here, let me define the new coordinate system is x prime, y prime. And the angle is theta. Okay. So the transformation, basically, usually we expand, we express is this. Usually is this. This is a point, for example, this is a huge, the elastic object. And if you'll be interested at one point, usually we did is we take a small patch and we try to extract the information about the patch. So that this one we call, this is called the stress element or patch, and which is used to describe the distribution of the stresses. Okay. And for this patch, we can give any just patch onto it, and then we can define any coordinate system you like, for example, x, y, or another student like to define his coordinate system like this one, and arbitrary. So that's the reason why we study the transformation, try to accommodate the different coordinate systems. So usually I suppose I need to overlap the stress element at the same point onto this plot, but that's going to mess up. So usually we try to extend our drawing outside here. We put into here, this is x prime, y prime. Okay, so that is the representations. But usually you have to keep in mind this point basically it should be at here. They talking about is the same local site. Okay, so for here we want to calculate. This will be the function of the theta. The same thing. This will be the functions of the theta. The same thing for the shear stress. And this is the x prime, y prime, the function of the theta. And again, on the two sides, they are symmetric. So for these questions, we want to know what are these. And let me quickly get the result here. Okay, we have the formula, and the formula based upon the equilibrium equations. And that one, let me give you this result here quickly. So here are given theta, sigma x, sigma y, and tau xy. We're going to find the prime. Okay, so that one is sigma. Let me go to this one first. And please leave a space, a line in between, because later I'm going to insert another simplified equation. And again, here you leave a line here, okay? for this one, we might be able to utilize, for example, if you like to utilize the MATLAB for using the matrix calculation, you might be able to write down these simple equations. That'll be easier. So here is sigma x, sigma y, tau x, y. So basically the first equations is writing up this one and put into the matrix multiplication with the vector. Basically here those are the coefficients and get into the term here, right? Okay, so that one I'm going to fill in. That is cosine squared, let me use c squared. Okay, so here the c defined is cosine theta. Okay, so cosine squared times sigma x. The second one is sine squared times sigma y. The final one is 2 times cs, right? Okay, and the second row is this one. Then again, here is the first one s squared. The second one is the cosine square. The last one is minus 2 cosine and sine. The last one is minus sine cosine and sine cosine. And then this one is c squared minus s squared. Let me check. So this one, if you wish, maybe you can utilize this one. You can write a very simple MATLAB program, and this is the right-hand side. All the terms on the right-hand side are given. You can quickly calculate those things. Okay, that's for calculations. And then again, for here, the sign convention is this. Theta positive for counterclockwise rotation, otherwise negative. And for compressive, for tension, sigma x or sigma y, they are positive is when they are tension, or otherwise they should be negative. And tau x, y, the positive negative should be in this way. I forgot. Let me check. Sorry, making you sleepy. This is positive when this is the plane, right? And this is the direction. When both positive or negative, they positive. Let me make one example. So this is a stress element. This is the x-plane, which means has a normal to the x direction, pointing to the x direction. This has an outbound normal to the positive x direction, so this is called a positive x-plane. So this one is called the negative x-plane. Because this one has pointing to the negative x direction. So under these situations, in the positive x-plane, this one pointing to the positive y direction. So this one is, this tau is positive. Okay, so another example is like this. Again, that will depend on our corner systems. This one in the x direction, positive x direction, pointing to negative y, so this one defined as negative. Okay, and the other one, in the negative x direction, the x plane, pointing to negative y direction, so this is positive. Okay, so that is the sign convention for this one. So once you're going to use the numerical calculations, put a sign onto each terms here. Okay, and so that is for the numerical calculation. This formula will be used later on once we talk about the transformation of the stress and the strain on the composite, and we're going to revisit this equation. I'm going to mention that one to that point. And to apply to the more circles will be more useful to put into using these equations here. I'm going to fill that underneath. So this equation can be also rewrite by this. We simply utilize the trigonometry, so that means 2 sine theta cosine theta equal to sine 2 theta, and then cosine square theta minus sine square theta equal to cosine 2 theta, and then cosine square theta equal to 1 plus cosine 2 theta divided by 2, and then sine square theta equal to 1 minus cosine 2 theta.